share slides. Okay. So it's my pleasure to welcome Beniamino Barberi. Beniamino's been in the country for 20, 30 years now. He came from Italy, where he, as an undergraduate, studied physics at the University of Pisa. And he is the president and founder of ISS, local company of manufacturing, prototyping, one-off instrument and that kind of stuff. So it's a pleasure to have him here.
All right, thank you, Scott. Good morning, everybody. I hope you had a nice evening, the first evening in Champaign. Did anybody go to Chicago last night? I came back this morning. No. Okay. So yesterday we started talking about fluorescence. Today we will talk about the application of fluorescence to microscopy, which goes under the general name of fluorescence microscopy. How many of you is using or working with a microscope? Several, great, very good. So we saw the definition of fluorescence yesterday, and there are several types of microscopy, and that's very interesting. I don't see the light here. I had a whole listing of here, it's just too fuzzy. So there are several microscopes and several applications of microscopy. The fluorescence, believe it or not, is on this line here. There are, of course, electron microscopes, atomic microscope, different techniques, Dick, phase, but we will focus only on the fluorescence microscopy. And specifically, I will talk a little bit about fluorescence microscope, and then go into the confocal microscope, which is a subset of the fluorescence microscope, and mention about the application of multiphoton microscopy. So, what is a fluorescence microscope? It's a microscope that uses fluorescence to generate an image of the specimen. So in other words, we use one of the probes that I mentioned yesterday in the talk to tag a protein, a molecule in the sample under study. We excite using light the particular probe, so it has to have the excitation wavelength has to be absorbed by the probe, and we detect the fluorescence. So the image is detected is an image in fluorescence. There are two general geometries for the fluorescence microscope, an upright and an epifluorescence. And this is the general schematics of a fluorescence microscope. So we have a light source, and the light is sent out to this optical device called a dichroic beam splitter. And this has the particularity of reflecting the excitation light down to the specimen. The specimen absorbs the light, re-emits the light. The fluorescence, which occurs at longer wavelengths, like we learned yesterday, is transmitted through this optical filter or dichroic beam splitter. And it reaches all the way the eyepiece or where we have our detectors. So this is called an upright geometry because the light illuminates the sample from the top down. Of course, in biology, it's more convenient when working with solution to come from the opposite end, and that is called an inverted microscope. But this is just a matter of geometry, of convenience. Now, let's go back here. So we talked about these two different geometries, and there are two general illumination schemes, the full field and the confocal. What is the confocal? The confocal is just a fluorescence microscope where there is a pinhole placed somewhere in the detection channel. What does the pinhole do? If we don't have a pinhole, what we image is the specimen, but we image also points that are outside of the focal plane of the specimen, of the image here. And this produces an image that is generally fuzzier or not crisp. By the introduction of the pinhole, we actually look at a region that is fairly confined. So it's about 1 micron in Z, and is about 300 nanometers lateral resolution. So the image is much crispier and clear. Just to give you an idea, because we have to put everything in perspective, the fluorescence microscope was introduced around 1910. The idea of the pinhole, the idea per se, was suggested in 1957, 1958. The first confocal microscope was built in 1986, 87, so 30 years later. And this is a cartoon that depicts what happens when you add the pinhole. You actually confine your observation volume to this region, about 1 micron, about 300 nanometers in lateral resolution. This is interesting. Yesterday I mentioned about the fact that it is possible nowadays to look at single molecules fluorescence, something that 20 years ago, 30 years ago was almost unthinkable of. Well, this is due to the combination of using the laser and this type of techniques. If you do a little bit of calculations, if you have these volumes, so 1 micron, 300 nanometers, and you have a solution of 1 nanomolar concentration, on average, within this volume, which is actually 1 femtoliter, so 10 to the minus 15 liters, on average, you have 1 molecule at a time. So this is a technique that enables you to follow 1 molecule, so a single molecule detection. So to go back to the historical perspective, it's like what Zernike wrote. This is part of his lecture when he was awarded the Nobel Prize in physics. And he is the discoverer of the phase contrast. So again, the fluorescence microscope was introduced in 1910, the idea of the pinhole, 1957, the first construction, 1987, the first commercial microscope, 1990. And so now everybody is doing confocal microscopy. Let's move on. So these are some of the pictures that you get with confocal microscopy. Very nice and sharp images. Now, how do we get there? So a typical microscopy setup is fairly simple. So there is a light source, optics, light detectors, and then there is your sample. So in the following, we will focus a little bit on the optics, just to go over some of the concepts that some of you who is working in microscopy are already familiar with. So we will touch a little bit about the structure, the objectives, the illumination, and then again we will move to fluorescence microscope and confocal microscopy. This is a picture of a microscope that is actually sold by Olympus, or used to be sold. And it's a fairly complex machine, but it's fairly typical of a microscope. So here we have the light source. The illumination source goes up here. The sample is placed on the stage, which typically moves XY. And we have several optics here to make sure that the beam is focused on the specimen. We have one objective which collects the fluorescence, and typically there is a carousel where people mount additional objectives. A beam splitter or a prism separates part of the light into the eyepiece. Part of the light goes to the detector, where we can have a light detector, we can have a film or a CCD camera to record an image right now. So basically a microscope uses a lot of lenses. So let's look a little bit about what happens in a lens. A lens is just a piece of glass. Sometimes it's a complicated piece of glass because there are 2 pieces or 3 pieces glued together. And if you illuminate from a distance, there is a point where the light converges, and this is called the focal plane. And then there are different types of lenses. There are lenses that converge, lenses that diverge, and so on. Then there are so many problems with the lenses, because these are some of the problems that need to be addressed, and these are affecting the quality of your images. And they are due to the fact that the refraction is not occurring the same at all the different wavelengths. And so there are a lot of these issues. Another useful parameter that is important to master when in microscopy is the numerical aperture, which is simply the sine of this angle here. So what happens is that if you have an objective with a high numerical aperture, this angle is higher, and you collect more light. Another number that you encounter in optics is the f number, which is equal to f, focal length, divided by the aperture. And you can relate it to the numerical aperture by this relationship. And this is the same numbers that is also used in photography when people are talking about fast lenses, or slow lenses. Basically, it has to do with the numerical aperture and the capability to collect the light from your optical system. Ideally, you want to collect as much light as you want, as you can. So you want to use an objective with a high numerical aperture. But then there are some practical limitations by doing that, because that affects the working distance, how far away you can actually get your signal from. Another important parameter is the resolution. So if when light goes through a small aperture, there is a phenomenon called diffraction, and the distribution of the light intensity follows this function, which is called the Airy function. And the Airy function has tells us that there is a lot of light concentrated around the zero. And then there are these rings, so the light goes to zero, and then there are additional intensity coming out here. And the position of the first dark ring, so when there is no light, is actually equal to this number, where this is again your numerical aperture, and this is the wavelength. From here, there is the concept of the resolution. So if we have 2 points, how close they can be in order to be resolved as 2 rather than 1. And this is the so-called Rayleigh criterion, and it relates the distance between the object, the wavelengths, and d, which is the aperture of the optical system. A third parameter is the contrast. The contrast of an image is much more simpler. It's you take, let's say, your image, you take the background, in this case is white, you divide it, and then you subtract it, and then you divide by the background. So you're interested in getting images with a high contrast rather than with low contrast. Now, let's see a little bit what's happening with the lenses when the lenses image an object. So if we have an object that is far away and the object is illuminated, the light, the image of the object, occurs in the focal point of the length, and is inverted, is right here. If we place our object closer to 2 times the focal distance of the lens, we get an image on the opposite side of the same size, and is upside down, is a real image. If we get it closer, so this is about 1.5 times the focal length, the object is magnified on the other side. So this suggests us a little bit how the microscope in principle works. So the microscope, we have a specimen here, and we have an objective, which this is the illumination source that it goes on the specimen. It produces an intermediate plane here, and when we place our eyes, so our cornea up here, we project an image of the real image here down at about 25 centimeters, and this is due to the curvature of our cornea. And so this is just the principle of how the microscope works. In reality, the microscope is obviously a little more complicated. First, after the objective people introduced another lens, which is called the tube lens, in order to have the light in a parallel beam between the objective and the tube lens. Why is that? If it's parallel, we can introduce optical elements such as filters, other optical elements. We can deviate part of the light. Each manufacturer uses a particular tube lens, and I don't remember in the order, was Zeiss, Nikon, and Olympus. Each one has his own distance. Now, the objective is the core of the microscope. The objective is fairly complicated. It's not one single lens. If you look at an objective, this is an icon. You see that it looks, this is the picture, and it has a number of information on it. The manufacturer, the origin, the type of objective, plan apo, 60 times, which is the lateral magnification, the numerical aperture, oil, and I will go back to that, why oil rather than water or air. What is the specialization of the optics? The tube length, infinity correct. The cover slip, the thickness of the cover slip that we need to use on the sample, so 170 micron. The working distance, 210 microns. And the magnification code, then there is a spring loaded. So if we look at the objectives, they are generally classified into 4 classes. And these are just the breakup of some of these objectives, the achromat and the plan achromat. As you can see, inside an objective, there are so many optical elements, so many lenses, and some of these lenses are glued together. So it's fairly complicated, which also translates into the price. So an objective that is oil immersion might cost $4,000. A water immersion 60 times, it might cost $10,000. They are actually coming out with objectives to study tissues now at depth, and they are projecting the cost at about $20,000, $25,000. So overall, the microscope is not a cheap instrument. You can start with $30,000. You can go all the way to $120,000 or $130,000, depending upon the automation, the number of objectives, the number of accessories, the lamp that you use for illumination. So this is just a complicated system. It's not a system, but it's a system that gives us a lot of nice images. So let's go back to the resolution a little bit. The resolution is equal to this number that we can simplify. So we have the wavelengths, and we have the numerical aperture, and then again the numerical aperture is here. So what this tells us is that the resolution is better if we use a shorter wavelengths and higher numerical aperture. The numerical aperture cannot be more than a certain number because of this angle between observation point and the lens. We can increase it a little bit by changing the index of refraction. And that's why the objective before had oil on it. Oil has an index of refraction higher than water, and so then we can go to a 1.5 rather than 1.3. And so we can increase our numerical aperture and improve the resolution of the image. This is a table that gives you some idea about the resolution that you can reach with different type of objectives. 10x, this is the magnification and the focal length. With oil, 100 times, 63 times. So your resolution, just plug it into the formula before, is about 200 nanometer, and this is the best resolution that you can get using this microscope. Nowadays, well, in the past 6-7 years, people have been talking a lot about super resolution. So there are ways to go below this resolution. And where this is 200 microns, with these super resolution methods, we can reach nanometers, we can reach 40 nanometers. It's nothing that defeats the physics. The physics is undefeatable, is inside this formula. But there are ways or techniques that allows us to go below this resolution. Let's talk a little bit about the color illumination. Practically all of the microscopes that you find today on the market use this color illumination, where the idea is that instead, when you have a light source, instead of imaging, illuminating on the sample, you illuminate with parallel beam the sample, and this increases the image. And so you can see here your illumination, it goes out. The sample is here, but it's a parallel beam because it's focused in this point before the sample. And this is another piece of importance in the microscope, the dichroic filter, which in the cartoon of the microscope is the one that allows the light from the illumination to be reflected down and the fluorescence to be transmitted. So typically when you buy a dichroic filter, you see this type of information, the transmittance. So in this case, the transmittance starts around 500 nanometers and above. So what it means is that we can use any wavelengths before 500, like in this case is optimized for fluorescence, so we say excited 488 nanometers. The light hits the dichroic mirror, is reflected down to the sample, the fluorescence comes up, the fluorescence occurs longer wavelengths, is transmitted through the dichroic mirror, and it finishes up into the detector. We can add a filter here that isolate further the laser line if the laser line has some spurious wavelengths. And we have a filter here if we don't want to acquire the entire emission spectrum, if we want to acquire only a portion of the emission spectrum. So we can add these filters. So this cube idea was introduced about 1950, 1960, and is still in use today. So it's an idea. So the real invention was how to build these optics, this dichroic filter, or this part of optics. And finally, a few words about the cover slip, which are very important. So you need to use a cover slip of the proper thickness when that goes with the objective that you are using for your measurements. Otherwise, you cannot just see the sample. And well, these are a few of the strengths of the fluorescence microscope, and these are some of the images that you get with the fluorescence microscope. Now, let's move over to the confocal microscope. So, confocal microscope was built the first time around 1985, 86 in some laboratory. The first commercial was actually 88, 89. And these are some examples of images that are collected with the fluorescence microscope and with the confocal microscope. You see that, for instance, a fluorescence microscope, you see this image that is kind of fuzzy, but the confocal microscope, you see some of the structures with a higher resolution. And just because you reject the light that is not at the proper focal length or on the same focal plane as the structure that you want to illuminate. These are additional images that show the difference. So on top we have images of fluorescence microscope, and these are images of confocal microscope. This is pollen, for instance. So you see the fluorescence microscope, this is the image, and this is the confocal microscope. So again, this is a fluorescence microscope, and the confocal microscope has this pinhole placed up here, which allows you to isolate and focus on a small volume here on the specimen. This is a cartoon that gives you, again, an idea of the differences between a wide field illumination in a fluorescence microscope and in a confocal microscope. Now, there are other ways to produce the confocality. And when I say other ways, I refer to not necessarily using a mechanical mean, like a pinhole, to isolate the plane of observation of your sample. These other ways are the two-photon excitation, and there are additional laser techniques that are being used today. We will focus on the two-photon excitation, or also multi-photon excitation, because people also use 3 photons. So the two-photon excitation works. Works at this point here. So it doesn't work on the area of the optics, but it's mostly on the light source. And something that I want to point out is also the fact that whenever we collect an image, the image is always is not the proper image of an object, but since there is a translation between the object and the image, there is in between what is called the point spread function, which is introduced by the entire element, but first off by the illumination source of our system. The point spread function depends upon the type of the laser that we use. If we use a single photon laser, this is given by this expression. If we use a multi-photon laser, it's given by this expression. So what this means is that while in XY, the laser profile is described by this function, in Z is described by this other function. This is important when we need to characterize our excitation volume, and we need to apply what is called a convolution technique. These are some examples of point spread function for a standard illumination for a fluorescence microscope, for a 2-photon and a 1-photon with the pinhole. So I don't go into this type. Let's go into the resolution of the confocal microscopy. The resolution is given by this formula, which resembles the formula that we saw before. And this was introduced by Abbe, who was a fellow who was working at Zeiss in 1970. And again, this is how close 2 points have to be in order to be resolved. And this tells us that we need to go to lower wavelengths, we need to increase the numerical aperture, or increase the index of refraction. And
this resolution is there in normal microscopy, like confocal?
Yeah, it's a confocal microscope. So as I mentioned earlier, we call it super resolution every method that go below this type of resolution, or what is called the Abbe limit. Let's go back to the 2-photon. Yesterday, we introduced the Jablonski-Perrin diagram, showing the ground state of molecules and the first excited state of molecules. And we said, well, the fluorescence is caused by the absorption of 1 photon in the excited states, and then the re-emission of the photon from the lower state of the first excited states down. Now, in quantum mechanics, this process is called a 1 photon, but the probability that also a 2-photon process occurs is not 0, and is actually can occur. So in other words, if here we need 4 photons of 400 nanometers to reach this level, we can reach the same level using 2 photons of 800 nanometers each. Why is that? Because the energy that is carried by a photon is proportional to the frequency, or inverse, of the wavelengths. Now, by doing the calculation, this effect, calling the 2-photon effect, has a very low probability, but and this is the cross section, and is defined as GM by Guppermeyer, who described the effect back in 1933-34. And this was never used until pretty much 1990, when pulse lasers became available. So in order to increase the probability of this effect, you need to concentrate a lot of energy into a short time. So there are these lasers called titanium sapphire, but we can use other lasers, where the pulses are very narrow, are of the order of 10 femtoseconds. And the power, the energy in each pulse is fairly high. So then the probability that this phenomenon occurs is fairly high. What is interesting about the two-photon process is that, okay, I guess I have a slide, is that this effect, the two-photon absorption, only occurs in a confined spatial region. So it's not a large spatial region. And this introduces, let's see if I go back here. Yes, this is a classical image that was publicized by Brad Amos. We have a cuvette with rhodamine, and we have an objective that sends light at one single photon. So the light is absorbed and re-emitted, and you see a straight line going through the cuvette. It's about 10 millimeters here. And this is one photon excitation. Down here, we have a two-photon excitation, and you might see a little dot right in this point. And that is the area where the two-photon excitation occurs. So the difference between one photon and two photon from the practicality of use is that while the one photon occurs into an enlarged area, so over the length of the 10 millimeters, the two-photon excitation occurs only in a small volume. And the small volume is almost as small as the resolution of the confocal microscope. So what we can achieve using the pinhole with the confocal microscope and the one-photon excitation, we can achieve using the two-photon excitation without using the confocal microscope. There are other advantages in using the multi-photon, and is the fact that since you use radiation at 800 nanometer, if you study tissues, this is your excitation. The radiation, tissues are pretty much transparent to this radiation. So you excite a probe at 400 using the 800, and so you don't cause interference between the excitation and the emission. This is the typical setup of a two-photon microscope. So again, we have our objective, the dichroic mirror. We have the laser, and we have some lenses, some optics. So the light goes in, and the light is collected through the dichroic down into the light detector, where we have the photomultiplier tube. So in this case, we don't have any pinhole at this position here. This opens a lot of possibility, especially in tissue spectroscopy, and but also in biology to study cells. Then again, because you use 800 nanometers, so you go more into the cell, but especially in tissue because you can go deeper into the tissue. Today, the limit to go into the tissue is about 500 microns, and it depends on the tissues, brain, liver, but you can go 500 micron into the tissue, although there are pushes, and I guess there is a lecture probably next week, Chris Xu, where he shows how you can go to 1.5 millimeters. So this just to give you an idea how the fluorescence microscopy can be used, starting with a standard fluorescence microscope, moving to a confocal microscope, and moving to the multi-photon microscopy. And here there are issues about maximizing the sensitivity. But the main message is that it depends at the end on your specific applications. And today, the technology enables you to push forward some of these limits and push the limits not only that deal with the limits of the diffraction of the physics, like the Hubble limits, but using the super resolution techniques to push the resolution of your images from the 250 nanometers all the way down to 40 nanometers. So that is pretty much here to talk about fluorescence microscopy. Any questions? Yes.
You showed the observing space contrast and talked about confocal. I didn't quite understand what is the relation between these two.
Sorry.
In the beginning of slides, you had the phase contrast technique, observing, and then said something about confocal and what was the relation between those two?
Nothing. It was just a citation, and I just wanted to point out how the concept of fluorescence microscope was introduced more than 100 years ago, the confocal, after 60 years. And this was just his observation of how some of these ideas are really slow to mature, coming to light, they are two separate things. Yes?
You had mentioned field pattern. So what is the purpose?
Sorry, again, the field?
Go back. Field pattern.
This one?
Yes. So what is the purpose of that?
To eliminate some reflection or scattered light that come out from the optics, but it's typically a field aperture, so it's not a confocal. It might be 1 millimeter diameter, 500 micron diameter. Sorry, again,
If you talk about structure,
yeah. Yes.
Can you talk a little bit about the widespread function of the pinhole, roughly what it looks like?
Yeah. So you use light to illuminate an object, and then you collect the image of the object. So the point spread function describes the general distribution in space of the light source that you use. And it's important, for instance, when you calculate the volume using two photon for fluorescence correlation spectroscopy, you need to give a description of that. You need to characterize the shape of the point spread function in order to get the volume of illumination of your sample. It depends if you use a single photon laser excitation. Is a 3D Gaussian, so it's Gaussian, lateral, and it's, if you use a multi-photon excitation, it's Gaussian lateral, but it's Lorentzian on the z-axis.
Okay, so I'm just kind of curious what the timescales involved in acquiring a confocal fluorescence image are.
Sorry.
I'm curious, what are the timescales involved in acquiring a confocal fluorescence image? So how many seconds does it take to take a picture of a cell?
Okay. The standard, so you see here, there is it's called an XY scanner. So there are different ways of doing the scanner. One is you can move the same force, but typically it's using a piezo, it's fairly slow. The other way is just to use galvo mirrors.
So the beam goes to two different mirrors. One scans in X, the other
other one in Y. And just to give you an idea, each pixel of the image, you may stay 4 microseconds. So the way it works, you divide your image, let's say 256.256 pixels. At each one you stay 4 microseconds, and then you do a raster image, so you do another line, another line, another line, another line, and you acquire the photos. At the end, what is important is the signal to noise ratio, so how many photons you acquire. And for some analysis, and you can use FLIC, fluorescence lifetime, you need about at least 1,000 photons per pixel. So what you do, you acquire an image fairly fast, and then you keep acquiring images. Now there are ways to acquire faster images. In fact, there are microscopes with galvo resonators. You can acquire even 1,000 of frames per second. Then of course there are the CCD cameras where they're also fairly fast.
So you can get 1,000 frames per second as you're scanning?
This single molecule detection, it's about the sensitivity of the detection or it's about the resolution?
Well, it's about the number of photons that you get out of the molecules. So when you do the experiments, you need to first select a good fluorophore, meaning a good quantum field. Remember yesterday we talked about quantum. And then, yes, you need to maximize it. You cannot use too much light because otherwise you will bleach the fluorophore. You need to have a good detector. A good detector, I mean, see, this a detector with a good quantum field. Typically, our large photodiodes can reach 40% quantum field. So when you do single molecules detections, yes, you need to optimize several parameters.
Okay. Any other questions? Any questions? Let's thank you. So we'll have just a minute if anyone needs a break, and then we'll resume in 15 minutes. Okay. Who's next? Is it me? Okay. Ken's next?
You got it. Oh, you wait for it. No, I